Okay, so I decided to do the stoichiometry worksheet. Actually, do a video on the answers. I sent you out a Word document, sort of describing it, but it's always better. I feel if I was in person, I would show you actually how to do it. And so I think this will be as kind of a substitute, and hopefully you'll see how to work these. Okay, and this will be. I don't know if you've had chemistry before. You may have learned dimensional analysis and all that, and that's okay. If you want to use it, use it, and there's no problem with it. Just gotta make sure you get the right things. Whatever works for you. Okay. Um, I'm gonna do it my way because it's more intuitive to me than using dimensional analysis. Okay, so if you want to use it, hopefully you'll be able to translate what I have here to that, and I will make comments where how you can do that. All right, so these are just the key points that you need to know as you do these problems. Okay. All right, so the first problem says you have 5.21 mils of liquid hexane and it's combusted in the presence of excess oxygen. The question is how much carbon dioxide gas is produced and how much liquid water will condense from this reaction. And so we're going to have to know the density of hexane in water because we're going to need to have, we have mils of liquid. Okay, it's not a solution, it's a liquid, pure liquid. So we'll have to figure out it's how many grams there is, because once you figure out grams, you can figure out moles. So whenever you have a liquid, pure liquid, you have to use density. So you go from volume, okay, to grams using density, okay, and then you will go from grams to moles using molar mass, okay. All right. Okay, so we're going to have to know the density. So we're given, so we have to know the density of liquid hexane to figure out how many grams it is. And then from that, we can figure out how many moles. Because this table here is always going to be expressed in terms of moles and moles per recipe. And recipes, okay. So this table is key for how we're going to figure out our answers. We're always going to want to get answers in moles and then figure out recipes using the moles per recipe. Okay, so we don't need to find a limiting reagent, okay, because we know that oxygen is in excess. So we don't have to worry about this, okay? or this. We have more than we need. So we know automatically that hexane is limiting. So the first thing I need to do is find this right here. I need to find the moles of hexane, and that's the first step. So to find the moles of hexane, we have to use the density and the molar mass. Okay, so first thing we need to do is find the grams of hexane using the density. So the density of hexane is 0.655 grams per mil. I looked it up. Okay, every mil is 0.655 grams, and I have 5.21 of them. So it's going to be 0.655 grams, 5.21 times. So you have 4.1 grams of hexane. Now, if you look at this, is how you would set up the dimensional analysis. Well, it'd be 5.21 mils times what you would call the conversion factor, which is density, and you have mils on the bottom, and they cancel out, you end up with grams, and so that would work. Okay, now we have grams, and now we have to figure out how many moles of hexane that is. Well, to figure out moles, you have to know the molar mass. So to figure out the mole of hexane is easy. You just there's 6 carbons and 14 hydrogens. You add them all together, and you get the molar mass. 1 mole of hexane is 86.2 grams per mole. Now, I like to think about it is that to figure out moles, you divide by the molar mass. Okay, so that's what I do here. I take grams and divide by the molar mass, and I get the moles of hexane. Now, if you were going to use dimensional analysis, you would go 3.41 grams of hexane. Okay, this is your conversion. Okay, and we want to have grams on the bottom, so we have 86.2 grams on the bottom, and moles on the top, and they cancel. The grams cancel out. You end up with the same answer. Now, if you notice, this operation is the same as dividing. All right. Okay, so either way you do it. So this amount, 5.21 mils, is the same as 0.0396 moles of hexane. All right. Now I want to know how many recipes can you make from this. Okay, so every time you do the reaction, you need 2. And so you can divide this up into 2 to figure out how many recipes. So this is how many recipes you can do with 0.0396 moles of methane. All right. Okay, and we just bring that over here. So that's how many recipes we can make of both of these. All right, so now what we're going to do is finish up this table, and then what we'll do is we'll use this information, figure out how many moles, and we'll figure out how many grams and so forth. All right. So don't worry about anything else. We just have to figure out the moles of carbon dioxide and moles of water. So if you have every recipe, there's 12, and you you're going to do the recipe 0.0198 times, you're going to have this many moles of, so you multiply to figure out how many, divide it over here going up, and multiply going down. And so this is how many moles of carbon dioxide, and this is how many moles of water. 0.0198, 14 times 0.0198. All right. Okay. Now what we have to do is come up with our what we need. What it's asking us. Okay. It says how much carbon dioxide is produced. Now, I should have asked you how many liters. Okay, so how many liters of carbon dioxide will be produced? And it maybe should have been more explicit at 25 degrees Celsius, 1 atmosphere. All right. So we're using a gas. Okay. So we're going to use remember when we're using gases, we're going to be using the ideal gas law. All right, so I want to figure out what is the volume of carbon dioxide gas that is produced. Okay, so I want to figure that liters. So this right here. All right, so I take the ideal gas law, which is PV equals nRT, and then rearrange the equation for V, and then I plug everything in. So I have 0.237 moles. I'm leaving the units out here, but they'll all work out if you cancel them out. Times the units, the universal gas constant was 0.0821 liters, atmospheres, Kelvin, -1, moles, -1. The temperature is 298.15. You can figure that out by adding 25 to 273.15. And then we're going to divide by the pressure, which is 1 atmosphere. And we get 5.8 liters of carbon dioxide. So when we combust 5.21 mils of liquid hexane, it will produce 5.8 liters of carbon dioxide gas. All right, now we want to find out how many mils of water are condensed or formed in this reaction. All right, we know the amount of moles is 0.277, and so I want to figure out how many grams that is. Okay, so what we're going to do here is that we want to find mils of water. We want to find how much what is the volume of the pure liquid water. So we're going to go from moles to grams using molar mass. And then since we're using a liquid, we're going to use density to figure out the volume, or liters, or milliliters. Okay, so we have 0.277 moles of water. The molar mass of water is 18.02 grams per mole. And if you do the math, you can see the moles cancel out, and you end up with 4.99 grams of water. So that's the liquid water will be 4.99 grams. All right. Now I want to know how much volume that takes up, and to figure that out, I need to know I have to know the density of water. Density of water, we're going to use 1 mil per gram. All right. Or probably the other way around, which is 1 gram per mil. And then what you can do is you can set it up like this, so density of water is 1 gram per mil. I just flipped it upside down so that the grams cancel out, and I end up with 4.99 mils of water. So when you get down, so if you combust 5.21 mils of liquid hexane, it would produce 5.8 liters of carbon dioxide gas and 4.99 mils of liquid water. Okay. All right. So this next problem says you have 75.4 grams of solid iron, and it's mixed with 500 mils of 1.51 molar copper 2 sulfate. So this is going to be a single replacement reaction. So I'm going to take the iron and copper sulfate, and I'm going to use one of them up first. So I have to figure out limiting, and the other one won't be used up. And then after I figure out the limiting, I can figure out how much product I make. Okay, so here's the chemical reaction. Okay, and so I'm going to figure out from this information up here. I'm going to figure out moles of each, and then I'm going to figure out which one is limiting using that information, and then I'm going to figure out how many moles of copper, and then figure out how many grams of copper. Okay. So first thing I need to do is figure out how many moles of the iron and the copper sulfate. Okay, there's 2 different processes here. First of all, you have a solid. Okay, when you have a solid, to figure out moles, you're going to use molar mass. Okay, I gave you a list about that. So when you have solids, you'll be using molar mass. Okay, when you use a liquid, a pure liquid, you'll be using density and then molar mass to figure out moles. Okay, if you're using aqueous solution, you'll be using molarity. Okay, and then if you're using a gas to figure out moles, you'll be using PV equals nRT. Okay, these are the key things for doing these. So iron's a solid, so we're going to use molar mass. Okay, so we start out with 75.4 grams, and you divide by the molar mass, 55.845. Right? I left the units out, but this would be grams, and this would be grams per mole. The grams cancel out with moles. If you want to use scientific notation, it'd be 75.4 times 1 over 55.845. So there'd be moles on top, grams on the bottom, and the grams would cancel out. All right, enough moles. All right. I always like to divide the grams by moles to figure out, molar mass to figure out moles. So I'll put that number here. I'm not done. Okay. Okay. Now I have to figure out how many moles of carbon dioxide, because if you have more than one of your reactants, you have to figure out if one of them is going to run out before the other. In the previous example, you were told that there was enough oxygen, so you didn't have to figure out the limiting. In the real world, you'll either have that scenario where you have always excess of one of the substances, or you're going to have to figure out which one is limiting and which one's excess. Okay, so I have to figure this number out. All right. I wrote it down here, but we just have to figure out. Okay, so to figure out the moles of copper, okay, it's an aqueous solution. All right, so what I'm going to use is I'm going to use molarity. Okay, I'm given 500 mils. I'm going to change that to liters. Okay, so divide by 1,000. So I have 0.500 liters, and the molarity is 1.5 molar, which is moles per liter. So then you multiply it, the liters cancel out, you're left with moles. And that's how you get this number here. Okay, so now you have both of your moles of your reactants. Now you have to see which one of these, which one you think you might be running out of first. Okay, so what you need to do is find out how many recipes each one will make. So independently of each other. So how many recipes will 1.35 moles make? Well, divide by 2. It'll make 0.6575 recipes using this amount of iron. Okay, now with this amount of copper sulfate, okay, divide by how many moles per recipe, and you can do the recipe this many times. Okay, so you almost could do 3 times as many recipes with the iron and copper sulfate. So you're going to run out of the copper sulfate first. All right, so what we do is that's actually how many times this reaction can be done. So we bring that number over here. And then we figure out how many moles of copper. Okay, so multiply, then we do 0.25, we do 3.252 times, and this is how many moles of copper that we're going to produce. Okay, now it's a solid, so that means I'm going to want how many grams that is. Okay, so this is the limiting here. Okay, I know I have 0.756 moles of copper. Its molar mass is 63.546 grams per mole. Okay, the moles cancel out, and you end up with 48.04 grams of copper. Pay attention to the states. Okay, we want to fill in the table with the moles, figure out the moles of everything, and then after that you find out whatever state using, if it's solid, molar mass, liquid, you'll be using density and molar mass. If it's aqueous or a solution, using molarity, moles per liter. And it's a gas, you'll use PV equals nRT. Next problem. How many grams of solid aluminum are added to excess sulfuric acid will form 43.2 liters of hydrogen gas? So what I'm going to be finding out is how many grams of aluminum, right? What I'm given is this many. I'm given the how much hydrogen gas is formed, and I'm told that this is in excess. Okay. All right. So for this one, so what I have to do is first of all figure out how many moles, which we'll figure this out now in a minute. Figure out how many recipes that is. Then bring that over here, because that's how many recipes need to be done. Figure out how many moles from that. And then we can figure out our information to figure out solids. We don't need to find a limiting because we're only given one of the reactants. Okay, so first thing I have to do is find out how many moles. So I need to find moles of hydrogen. Okay, it's a gas, so I'm going to use the ideal gas law. So N is moles. Rearrange the equation, so N equals PV over RT. Okay, I told you at the very first slide that the atmosphere is 1. All right, the volume is 43.2 liters. An universal gas constant, and the converted temperature into kelvins is that. Simply do the math, and you end up with 1.76 moles of hydrogen. Okay. And then, all right, we put that number here, and then we figure out how many recipes that is. So we divide that up into groups of 3. 0.587. Bring that over here. So every time you do it, you need 2. You only have 0.587 times to do it. So you multiply these together. And that's how many moles of aluminum. All right, so I have 1.17 moles. That's how. So if I have 1.7 moles of aluminum, it would produce 1.76 moles of hydrogen. All right, now I have to figure out how it's solid. So I'm going to use molar mass. So so the molar mass of aluminum, 26.98 grams per mole. The moles are 1.17. Multiply them together, it's 31.6 grams of aluminum. Right, so what this means is if you start out with 43.2 liters of hydrogen gas, 25 degrees C, 1 atmosphere, you would need to do that 31.6 grams of aluminum is in excess sulfuric acid. All right, next problem. How many grams of solid sodium are needed to add to 731.9 mils of 0.54 molar aluminum chloride to react with all of the aluminum chloride? Okay. All right, so what do I know and what I want to find out? So how many grams of solid? So this is what I am going to be looking for in the end, and it's grams, okay? And what am I starting out with? I'm starting out with this right here, okay? And I'm also going to want to find this one out here. Anything else? Nope. Okay, so that's it. All right, so first thing I'm going to do is I'm given this amount of aluminum chloride, and so I have to figure out how many moles that is. So here's what it is, but let me show you how I got that. Okay, so this is it says aqueous solution, so I'm going to use molarity to find moles. All right, 731. So I have to have, since molarity is in moles per liter, I have to change the milliliters to liters, so I divide by 1,000. So this is 0.7319 liters. The molarity is 0.540 moles per liter, and you can just see that the liters cancel out. And that's how many moles of aluminum chloride you have, right? And from that, you can figure everything else out. Okay, so what I'm going to do now is find out how many recipes I can make from that. Okay, so divide that by 1 mole per recipe, and so that means I can make 0.395 recipes, and I put those. You're only given one of the reactants, so you don't have to find limiting. All right, and so you bring this number all the way across. Okay, so next thing I want to do is find out how many grams of solid sodium. Well, I have to first figure out how many moles that is. So this is how many recipes I do, 0.395, and I do 3 times. So this is how many moles of sodium chloride I will need to react with all the aluminum chloride. All right, so what I do is I take the 1.19 moles. Okay, it's a solid, so I'm going to use molar mass, 22.98 grams per mole. And you end up with 23.74 grams of sodium. So that's how many, so you'll end up, so what you'll need is 23.74 grams of sodium to react with all of the with 731.9 mils of 0.54 aluminum chloride. All right, how much aluminum you're going to make? Okay, well, its number of recipes is 0.395. You have 1 mole per recipe. Okay, so you do that one time, and so this is how many moles of aluminum. Okay, so we're going to use, just like with the sodium, since it's a solid, you're going to be using molar mass, so it's going to be 3.95 moles times 26.98 grams per mole, and so 10.66 grams of aluminum are produced. Okay, so that's how you do it. Now, so I have the equations balanced for you. I'm not sure how. Then maybe you'll do that. You have that in your test. And remember is that the coefficients are the moles per recipe. Okay, so when I do these, what I do is I have the balance equation, and then I have this little mole recipe table, and then what I'm always going to do is I'm going to always fill in the moles to figure out, and then from that I'll figure out the associated states of matter and the values. Okay, so 9.3 mils of chlorine gas is added to 2.0 liters of 0.5 molar magnesium bromide. So this is a single replacement reaction, non-metal. And so since I'm given more than reactant, I have to figure out which one is my limiting. Okay. And then after that, I find out how many recipes I can make with it. And then I find out how much product. Okay. And of the beryllium I'm going to make. Okay. All right. Okay. So first thing I'm going to do is I'm going to have to find both of these values right here. I have them in there, but let me show you how I got them. Right, so I have to figure out the moles of the chloride and moles of magnesium bromide, figure out how many recipes each one can make, and then the lower one is how much you can actually make and how many times you can do the recipe. Right, so to find out the moles of the magnesium bromide. Okay, so I want to figure this out right here. Okay, so I am going to use molarity. Okay, so it says it's 2 liters, and it's 0.5 moles per liter. So it's just simply do the math. Liters cancel out, and then you end up with 1 mole. So this amount, 2 liters of 0.5 molar, is 1 mole of the magnesium bromide. Okay, now how many recipes can you do with that? Every time you need one, every time you do it, you need one. Well, you have one, so you can only do it once, okay? So you could do the math, but divide this by this, but hopefully that makes sense. Right, now let's look at the chlorine gas. Okay, chlorine gas, it's a gas, and I'm told that it's 9.3 mils of that gas. So I'm going to use the ideal gas law. So this is the volume. I'm going to want this in liters, so I'm going to divide it by 1,000. So rearrange equation for moles, N. So N equals PV over RT. So 1 atmosphere, 9.3 divided by 1,000. This is the ideal gas law, mean universal gas constant, and this is temperature. This should be K, right? When you do that, cancel out everything. So the atmospheres cancel out, liters cancel out. Okay, kelvins cancel out, and you end up with 1 over mole minus 1, which is moles. Right, so that's how many moles of chlorine gas you got. Now, how many recipes can you do with that? Well, you take the 0.00038 moles divided by 1, because there's a 1 in front of these, and then you bring it up here. Okay, so you have to compare these two numbers here. And we see that this number is much smaller than this, so this is going to be your limiting. So this is how many times you do it. So you bring it over here, and that's how much you'll make. Ignore that 0 there. Okay, so you can only do the recipe 0.00038. So that number comes over here. So how many moles of bromate you're going to get? Well, every time you do it, you need 1. And you can do that, this amount, that many times. And so this is how many moles of bromine gas liquid you're going to produce. Okay, so now what we have is we have moles, and we want to get that to liquid. Okay, so mils of liquid. So what we got to do is figure out grams using molar mass, and then we're going to use density to figure out mils. Okay, 2 steps. All right, so this right here explains the comparison of these two. All right, so first thing to do is figure out how many grams of bromine. Okay, so you have, this is how many moles, 0.00038 moles times molar mass, and just look up Br2. And so that's how many grams of Br2. All right, now what we want to do is so you have a liquid and it weighs that much. How much volume does it take up? Well, we need to know the density. Okay, and I have it written up here as dividing by the density, but you could also think about it as dimensional analysis. You have 0.0607 grams. Okay, this is the density. Okay, so we want to have grams on the bottom. So, and you look this up, by the way, or you're given it. So I gave it to you up here. Actually, I didn't. That's the wrong one. Per grams, mils. Okay, the grams cancel out. You end up with 0.0195 mils of bromine. Okay, this is wrong. All right. Okay, that should be 3.12. Sorry about that. Okay, maybe that confused it, but hopefully you'll see what I did here. So you could either divide by the density, or you could do dimensional analysis. You end up with the same amount. So what this says is if you start out 9.3 mils of chlorine gas, 2 liters of 0.5 molar magnesium bromide, you're going to make 0.0195 mils of bromine liquid. Okay. This then in the magnesium bromine's excess, and I don't ask you anything about the magnesium chloride. All right, next problem. How many grams of silver chloride would precipitate if 110 mils of 3.5 silver nitrate is added to 212.9 mils of 2.7 molar magnesium chloride? So this is a double replacement reaction in precipitation. So you're going to add a solution of this silver nitrate, solution of magnesium chloride, and what you want to do is find out how many grams of the silver chloride are produced. Okay, so what we need to do is, since you're given both reactants, you have to figure out which one is limiting. So we got to figure out this and this. Okay, and I got those numbers here, but let me show you how I got them. Okay, so both of these are solutions. So we're going to be using molarity. Okay, and we're going to have, if we're using molarity, we have to have this in liters. So divide by 1,000. All right, for the silver nitrate, you have 0.1102. That's this value right here, liters, times 3.5 moles per liter. That's the molarity. And when you do that, okay, you'll make 0.386 moles of I mean, that's how many moles of silver nitrate you have. That's to start out with. All right, how many recipes is that? Divide that by 2. And so you can do it 0.195 times. All right, now how many moles of magnesium chloride do you have? You have, divide this by 1,000, so it's 0.2129 liters. Multiply it by its molarity. And this is how many moles of magnesium chloride. Okay, how many recipes can you do with that? Divide by 1. And so you can do this many recipes. Okay, so compare the 2 recipes. Okay, and you can see that this is, you're going to run out of the silver nitrate way before you're going to run out of the magnesium chloride. You can almost do this reaction. You can almost use up 3 times as many of the silver nitrate for this amount. So this can be excess. So we're not going to use that. So that's how much silver chloride. How many recipes you're going to make? Okay. So we're going to do the recipe. Well, so end up doing the recipes 0.193 times. Every time you do it, you need 2. Okay, and so you'll do this twice, and so you end up with 0.386 moles of the silver chloride. Okay, so it's in grams, so we're going to use molar mass. So the moles are 3.386. The grams per mole, 107.87 for silver. I made a mistake here. Okay, this is not right. This is not the molar mass of silver chloride. Okay, let me get that for you. That's just the molar mass of silver. Okay, so 107.87 plus 35.45 twice, no, just once. 35.45. Okay, so silver's 107.87. Chlorine is 35.45. Add them together. So it's 140. So really this should be 0.386 moles times 143.32 grams per mole. And okay, so this is wrong. It should be 55.32 grams of silver chloride. All right. Sorry about that mistake. There's 2 mistakes in a row. Okay. This number's wrong. This is only for the silver. For the silver chloride, it would be 107.87. Silver chloride, 107.87 for silver, 35.45 for the chlorine, and so that's going to be 143.32, and multiply that by 0.386. Okay, hopefully you follow along with that. Okay, how many mils of 0.67 molar carbonic acid will neutralize 145.9 mils of 1.6 molar sodium hydroxide? So you don't have to figure out anything with the product. Okay, what you can do is what you're given is that you want to figure out. So you want to find out how many mils of the carbonic acid will combine with 145.9 mils, 1.6 molar, and neutralize it. Use it all up. So it's going to be a direct 1-to-1. It's going to be the ratio is going to be 1 to 2, okay, in terms of moles per recipe. So the first thing you need to do is, so you need to find out both moles. So, okay, so we can find this moles because we know we have molarity. Okay, so aqueous, and when you have aqueous to figure out moles, use molarity and volume. So you're going to change 145.9 to divided by 1,000. So it's going to be 0.1459, that should be liters, times 1.6 moles per liter. And then that's how many moles of sodium hydroxide. And then you have to figure out how many moles of carbonic acid will react with that many moles. Okay, so divide by 2. So it's 1.17. Bring it over here, so that's how many recipes you can do. And then how many moles you multiply. So this is how many moles of carbonic acid you need. Okay. All right. So I'm given molarity, and I want to find out volume. Okay. So what I do is I take this moles, and I have it. You can set it up this way, divide, or you could use dimensional analysis. So it's 117 moles. Okay. And the molarity is 0.67, so you put 0.67 moles on bottom, liters on top. Liters cancel out. And essentially, you're dividing 0.117 by 0.67, just like I did up here. And then you end up with 0.174 liters of carbonic acid. But you want that in terms of mils, so you multiply that by 1,000. And that's 174 mils of carbonic acid. So what this means is if you take 174 mils of this concentration, 0.67 molar carbonic acid, it will neutralize 145.9 mils of 1.60 molar sodium hydroxide. Key to this one, there's nothing to do with the reactant. You're just figuring out how much of the other reactant you need to use up the given. Right, so hopefully that'll help you out. The key things is write down your balance equation. Have your little molar recipe table. Put in your moles per recipes. Figure out. You always have a molar start. Okay, mole start, and you'll figure that out using. If it's a solid, you'll use molar mass. If it's a liquid, you use density and molar mass. Gas, universal gas law, another one, molarity. Molarity, you use the molarity. Okay, aqueous, use molar matter. Okay, and then you'll figure out whatever moles. And then you have to figure out the moles of whatever else is asked. And then you got to take those moles out and figure out grams, liters, milliliters, okay, and so forth. All right. So the key thing is to get into the mole table first from whatever grams and then come back out of it. All right. So you go into the table and then using whatever way to get to moles, and then you come back out of it, all right, after you figured out the number of recipes. Okay, hopefully that do you, and good luck. All right.